I'm going to remove these individual drag curves and leave just the total drag. I'm going to draw arrows from here to the drag curve at different speeds. This is our minimum drag, just so it's clear among these other arrows. And for example, let's say it's 65 knots, just for ease of numbers. And let's say this is 70, this is 75, this is 60, this is 55. Now to understand this, I'm going to draw a free body diagram, but we have to assume a few things. The first is in a glide, we're going to be in uniform motion. So we're not going to be accelerating or decelerating. Remember, acceleration is a change in velocity. And if we want to measure the drag at one velocity, we've got to keep it at that same velocity. So what that means is acceleration is zero and the net force is also zero. So all the forces have to be balanced. We're going to represent the airplane as a dot, just so it's easy to draw and it makes it a lot easier to visualize the forces. The one force that does not change when we're gliding the plane and we're changing the speed and the drag, the one force that stays the same and has the same direction is gravity. So that's always going to act straight down towards the ground. And the two other forces we're dealing with in a glide are drag and lift. Drag and lift are always perpendicular to each other. This might seem a little bit weird, but it will make more sense as we go. Like I said before, all the forces are balanced. So we have to make sure that gravity and lift and drag end up creating a net force of zero. To better visualize this, we can resolve gravity into its components. One component which is parallel but opposite to drag, and the other one that's parallel and opposite to lift. These two components also have to be at right angles to each other. They have to be. To help me draw this and to help you understand this, this will be confusing, but it will make sense in a second. Because these two components have to be perpendicular, we can draw here, we can draw a semicircle. And the reason is any two lines from the edges of the diameter match to make 90 degrees on the semicircle. It will make sense in a second. Let's come back to this diagram. In a glide, our goal is to have the most distance covered with the least height loss. We want this ratio to be big. And when that ratio is big, another way to think about it is that this angle, theta, let's call it, this angle is really shallow. Assuming this is right angle, of course. The same angle there, they're alternate angles. We want theta to be shallow. If we had a triangle like this, as you can see, it's very steep. We're not covering much distance and we're losing a lot of height. So that's our goal. Remember that. Like I said, gravity has to be resolved into perpendicular components. Let's draw our first diagram and let's use this arrow. Let's use this arrow at the minimum drag. Let's use it as a drag vector. The problem with this is, remember what I said, the component of gravity has to be parallel and opposite to this, like that, but it must lie on this semicircle. Otherwise, the components won't be perpendicular. So what I can do actually is use that same length and put it on the semicircle so it actually matches. Like that. And now I just have to rotate this arrow a little bit, just like that. Our component that's opposite to lift can be drawn in there, and then our force of lift can be drawn in like that. Right angles, these are right angles, and to label them, drag and lift. To find this angle, this is our glide. To find that angle, this is the horizontal line, and that's our angle there, theta. That is our descent angle. So no matter where the nose is pointing, we're going to drop like this. And we're in uniform motion. So our speed isn't changing. What happens? This is, remember, the best lift over drag speed here. What happens if I change my airspeed? What happens? Well, obviously, there's more drag. Either I go lower or I go higher, there's going to be more drag. That means this arrow, this drag force is going to increase. When this drag force increases, I can't just make this arrow longer and leave it like that. Why not? Well, if I was going to match this side, it lands outside the semicircle. This is not geometrically possible anymore. Instead, I've got to rotate it like that so that it works. And look what's happened. Don't worry about the lift there. That's also got to rotate. Look what's happened to theta. It's gotten bigger. That means descent angle has gotten steeper and we cover less distance. As our drag arrow gets bigger, it's also got to rotate to make this geometry work. And then our angle is bigger and our descent profile gets steeper. That means we need drag to be as short as possible, so then it actually creates the smallest angle. So that is a proof as to why this speed here, which gives us the minimum total drag, will also give us the shallowest descent angle and allow us to cover the most distance, because less drag allows a shallower descent angle, which gives us, once again, the most distance. I think this is a really cool proof. If you enjoyed this, please give me a follow. You'll see much more deeper aerodynamics and aviation content like this. As always, stay safe in the skies. My name is Rushil.